When a battery is pushed to its absolute limit, the physical stress is visible. It heats up and degrades, physically struggling against its chemical payload. Introductory physics often treats a battery as a flawless dispenser of energy. In reality, every power source is an imperfect system with built-in physical limitations. We model a real-world battery using two components: the electromotive force, E, the theoretical voltage, and internal resistance, lowercase r, representing physical friction. When a circuit closes, current flows. Before energy reaches the load, internal resistance consumes a portion, dissipating it as heat. Because every power source works against itself, the primary challenge is finding the specific conditions needed to overcome this internal bottleneck and maximize the output. Scaling this problem up complicates the math. A single battery is manageable, but high-demand systems require combining hundreds or thousands of these imperfect sources. To handle these loads, engineers arrange cells into a mixed grouping matrix, a grid that connects units in both series and parallel configurations. Simply adding more batteries does not result in linear performance gains. In a poorly configured grid, the compounding internal resistance will trap the majority of the generated energy, wasting it as heat within the system itself. We can use algebraic factoring and differential calculus to identify the exact threshold where this system performance peaks. Solving for the matrix identifies the precise mathematical ceiling of the entire grid, revealing how the arrangement of the cells determines the total available output. The model starts with a single row of n identical cells connected in series. This configuration multiplies the total voltage by n. However, this also causes the internal resistance to compound. For this single row, the total internal friction is now n times r. To build out the matrix, we take that row and duplicate it, stacking m total rows into a parallel configuration. While adding rows in parallel doesn't increase the voltage, it provides more pathways for the current to flow. This reduces the total internal resistance of the entire matrix to nr divided by m. Finally, we connect the entire matrix to an external load, which we define as resistance uppercase R. We can now define the system using Ohm's law. The total current, I, is equal to the total voltage divided by the sum of the external and internal resistance. This master equation dictates the flow of current. Our goal is to find the values that make this output as large as possible. To maximize the current, I, we must minimize the denominator of our equation. We start by multiplying the top and bottom by m to clear the fraction. This leaves us with the term mr plus nr in the denominator. This is the value we need to drive to its absolute lowest point. We can find that minimum by applying the algebraic trick of completing the square. We rewrite the expression as the square of the difference between root m, r, and root n, r, plus a constant factor. Since any real number squared must be at least 0, the lowest possible value this term can reach is 0 itself. By setting that squared term to 0, we find that mr must equal nr. Solving for r gives us the peak condition. The external resistance must equal the total internal resistance of the matrix. If we apply this to a practical problem with 24 cells, we can calculate the exact dimensions of the grid. In this case, 12 rows of 2 cells each provides the required balance. The algebra proves that maximum current is achieved only when the system's internal resistance is perfectly matched to the external load. Current is only half the story. In engineering, we are primarily concerned with power, the actual rate at which the load performs work. In a basic series circuit, power is defined as current squared times the external resistance, R. Substituting our earlier current formula into this equation gives us a function for power that depends entirely on the value of the external load. To find the exact peak of this function, we take its first derivative with respect to r and set it to 0. Applying the quotient rule results in a numerator where the derivative of the top times the bottom is subtracted by the derivative of the bottom times the top. As the algebra simplifies, the terms cancel out to leave one clear result. Power is at its maximum when uppercase R equals lowercase r. If we plug that result back into our original power formula, we find the absolute physical limit for any given source, the voltage squared divided by 4 times the internal resistance. Whether we use algebra or calculus, the conclusion is the same. The peak of system performance is found at the equilibrium point between internal loss and external load. This conclusion is the maximum power transfer theorem. It defines the point of optimal delivery for any electrical system. We can visualize this by plotting power against load resistance. As resistance increases, power output rises sharply to a peak before beginning a slow decline. The top of that curve occurs exactly where external resistance R matches internal resistance R. There is a significant trade-off at this peak. Because the internal and external resistances are equal, exactly half of the total energy generated is being lost as heat within the power source itself. This creates a mathematical conflict between efficiency and power. To get the most work out of a system, you must accept a 50% loss in efficiency. Large-scale electrical grids and high-voltage transmission lines are designed around these specific ratios to ensure that energy moves across the country without overloading the system. This balance is known as impedance matching. From microscopic processors to national power grids, the same mathematical constraint applies. To reach maximum output, the external world must be calibrated to the internal flaws of the power source.